Sometimes we find it impossible to solve a game completely by using dominance method only. This is our game matrix between C2 and C1. 2 is less than 4, 4 is less than 5 and 0 is less than 3. So with smaller members, column C2 dominates C1. C1 is cancelled. Part of game matrix we have now. In this matrix, between R2 and R1, 4 is greater and 0 is equal. Second row R2 dominates R1. R1 is cancelled. C2, C3, R2, R3. 4, 0, 0, 8. Now we have a 2 by 2 matrix, and this cannot be solved onwards by using dominance rules, because not any single row or column is dominating over any other row or column. In such conditions, we can apply arithmetic procedure to solve this game. And the very first step of arithmetic procedure is to find oddments. Difference between 4 and 0. Place it in front of the other row. Here. Difference between 0 and 8, 8, but place it here. Between 4 and 0, 4, place it here, below the other column, 4. And difference between 0 and 8, here. So we have 4 oddments, and with the help of these oddments, we can calculate our game value. Zero into 8 plus 8 into 4 divided by sum of these two oddments. So this is the procedure to obtain game value. And the value is 32 by 12 equals 8 by 3. 8 divided by 3 is our game value. Now this game value of 8 by 3 can also be obtained by 3 other calculations. This is the final 2 by 2 game matrix, and for the second calculation we can select the same oddment column, but this time with other column other than the earlier selected column. So this time we choose this one. Again we multiply corresponding values. 4 into 8, these values, plus 0 into 4, these values, divided by the sum of these oddments. And we have the same game value of 8 by 3. Third calculation. This time select the oddment row along with any one of the two rows, say this one. So 0 into 8, these values, plus 8 into 4, these values, divided by sum of these oddments, 8 plus 4. And we have the game value of 8 by 3 once again. Fourth and last method. Same oddment row, but this time with other row, this one. We need to multiply the values next to each other, and 8 by 3 again as game value. So this is how we can obtain a game value with 4 different calculations in arithmetic procedure. But we have to do it only once, not 4 times by all 4 methods. And now the section of optimal strategy. This time we are calculating probabilities separately. What are the steps to calculate probabilities? Let's see. The same oddment here, 8, divide by sum of these two, 12, 2 by 3. Here also the same oddment 4, divide by sum of these two again, which is equal to 1 by 3. Below the matrix, same oddment 8 by sum of these two, 2 by 3. And here also the same oddment 4 by sum of these two. So these are the probabilities, and using these probabilities we can define optimal strategy. First, for player A, first row R1 here you can see is cancelled, so 0 probability. For the second row, probability is 2 by 3. And for the third row R3, 1 by 3. And the same for the second player, player B. First column is cancelled, 0 probability for a cancelled column. C2, 2 by 3. And for C3, it's 1 by 3. Eight by 3 is our game value, and this is optimal strategy in fractional form. Second question, between R2 and R3, 5 equals 5, minus 10 is greater, and minus 10 is greater. So second row R2 dominates R3. R3 is cancelled. Between C2 and C3, 10 is less than 20 and minus 10 equals minus 10. Column C2 dominates C3. To solve this matrix, we can apply arithmetic procedure. And the very first step is to calculate oddments. Difference between these two, 15. And difference between these two, 15 also. Between minus 5 and 5, 10. And between 10 and minus 10, it's 20. So we have 4 oddments to calculate our game value. Into 15, 10 multiplied by 15, plus minus 10 multiplied by 15. So this will be 0. Divide by sum of these two, 15 plus 15 equals 0. Now the section of optimal strategy. And to define optimal strategy for both players, we need to calculate probabilities separately. Same oddment 15 by sum of these two 30 1 by 2 15 by 30 1 by 2 again. Here 20 divided by 20 plus 10 30 2 by 3 and 10 by 30. Sum of oddment will always be the same, so 1 by 3. So first for player A, R1 1 by 2 probability, R2 the same 1 by 2, and R3 is already cancelled, so 0 probability for a cancelled row. And for player B, first column 2 by 3 probability, second column 1 by 3, and third C3 is cancelled, so 0 probability. 0 is our gain value. This is optimal strategy. We had a look for complete procedure, and now we are going to discover this concept of mixed strategy with some examples. Why this term is called mixed strategy, and what are the basic differences between a game of pure strategy and a game of mixed strategy. Our first example is this is a game of pure strategy. Game value for this game matrix is 1. This payoff value 1. So how exactly we obtain this game value? Because both of the players, player A and player B, are playing a particular strategy. Player A is playing his second strategy R2. So the optimal strategy for player A is 0, 1 and 0. And for player B is playing his first column, C1. So optimal strategy for player B is 1 for the first column C1 and 0 probabilities for two other columns. So at the intersection of both strategies, this value of 1 is our game value. But in case of mixed strategy, like in this game matrix, our game value is 8 by 3. This is the same first problem we have solved in this chapter. And these are the optimal strategies. So you can see here, first player, player A, has two different strategic values, 2 by 3 and 1 by 3. So this indicates that player A is playing more than a single strategy. He is playing in the second row as well as the third row. And player B is also playing in the second column and in the third column. So basically this term mixed strategy is used when players are playing more than a single strategy. Here both of the players resorted more than a single strategy, and that is why it is called mixed strategy. Now the question is, why do they need to play multiple strategies this time? And why not only a single strategy like they do in case of pure strategy? And the answer is because this game value of 8 by 3 does not belong to given game matrix. You can see here, none of the 9 payoff values is equal to 8 by 3. So, in order to get a game value which is not the part of given game matrix, somehow they will have to manage a kind of average, you can say, of 2 or more strategies. 8 by 3 lies somewhere in between these values, and to reveal this game value, both of them are using their second and third strategies. Now, other important thing is, what is the ratio between strategies? The probability of 2 by 3 and 1 by 3 means player A is playing total 3 times here in one complete game, because we have 3 here. And out of 3, he is playing 2 times in second row R2 and only a single time in third row R3. And the course of action for player B is also exactly the same. He is also playing second column 2 times and the third column only a single time in one complete game. In this way, we can determine the ratio between strategies of any single player. Now the final discussion, how these three terms are related to each other: saddle point, pure strategy, and mixed strategy. Let's see. This is a given game matrix of pure strategy. And now we are going to apply the concept of saddle point in this game. First thing, minimum of each row. So this is maximin. And then maximum of each column, and this is minimax. So the intersection is saddle point, and our game value is 5 for given game matrix. Now once again, in the same game matrix, we are going to apply the concept of domination. That means the elimination of row and columns through comparison. So second column is dominating fifth. Fifth column is cancelled. Second column is also dominating fourth. Fourth is also cancelled. And this row is dominating all the others. So all the other rows are cancelled. And now payoff value in the middle cell is smaller than the two other payoff values. This middle column is dominating over the other two columns. Other two columns are cancelled. We obtain the same game value of 5, first by the method of saddle point and then by the method of dominance. So in case where there is a saddle point in given game matrix and we try to reduce it by dominance, then we finally get a single cell that is actually saddle point, and the payoff value in that cell is our game value. Now the other example is a game matrix of mixed strategy. First, we apply the concept of saddle point. First thing, minimum of each row. So this is maximin. And then maximum of each column. So this is minimax. And maximin does not equal to minimax, you can say here. So this game has no saddle point. Now we are going to solve it again, but this time by the method of dominance. This column is cancelled by dominance, then this row, again this row, and then this column is also cancelled. But now this 2 by 2 matrix cannot be solved by the method of dominance, and we have to apply arithmetic procedure. And after arithmetic application, we get the game value of 5 by 3, and optimal strategies are like this. And again you can see, because we have a case of mixed strategy, the game value of 5 by 3 does not belong to the given game matrix. So finally, we can conclude the following. A game of pure strategy that can be solved completely by dominance always has a saddle point. And a game of mixed strategy that cannot be solved completely by the dominance doesn't have any saddle point. We had a look for the same condition in third question of the second chapter. We were unable to find the game value by using method of saddle point, and for this game matrix the game value can be obtained by the arithmetic procedure and the players will have mixed strategy.